So here's another bit of information. This analyzing input data comes from one of these textbooks, and the big lesson here is that the machine learning is not really the source of all the intelligence. Humans are feeding a lot of intelligence into what happens here. So let me set this up in Google Colab. We're going to analyze some data about housing prices in California that came, I think, ultimately from some government agency. So let me get a new notebook here. All right. And so we import some packages again. sklearn is the package this time, another machine learning library. And then we're going to download this data of housing from California, some government agency. It's old, so the housing prices are a lot cheaper than they would be these days. But there's a data set from Ageron, whatever that is. And here's what you get: longitude and latitude of houses, the total number of rooms, and ultimately the house value. And what we're going to try to do is predict the value of a house from these other parameters. So we can use head to see a summary of the data, or rather to see the first 10 records of data, just like it would in. So here's what you have: longitude, latitude, median age, total number of rooms, bedrooms, the population. It's broken up into little zones, sort of like counties, and then number of households, the median income and the median house value, and then whether it's close to the ocean, factors that would affect the price of a house. So you can try to see categories and counts. To understand this last column, which is not numerical, we can, here's AI trying to help me and really just getting in the way. There we are, code. All right. So here you see there's 5 possible values of that alphabetical thing, 5 on an island and others near the bay or near the ocean or whatever else. All right, and we can get statistics of these things. And this is the thing. This is not put in by the AI. A human, if you have data you want to use, you have to heavily massage the data before an AI can use it. And we're going to see this quite a lot as we go ahead. If you just take raw data and try to train from it, you'll get bad results typically. So here's a summary: count, mean, standard deviation, and so on of these various fields. So you get an estimate of what you're dealing with. And then you can make histograms of them. And this is where you really have to do stuff that made me very nervous. As in the past, I was a research scientist, and the stuff you actually have to do in AI is troubling. So here's histograms. So as latitude and longitude is not a Gaussian, of course. There's 2 peaks. There's the San Francisco Bay Area and Los Angeles, and not much of anything else. So you get 2 peaks. The Howdy median age has this really strange structure. And notice this: a huge spike at 50. Well, that means the data is not accurate. Apparently, there was a maximum value, and anything over than 50, they just call it 50. So that huge spike is not really representative of the actual phenomenon you're trying to describe. It's a mistake in the data, and it looks like there's a problem at the value, too. 500,000 is the peak, and anything higher than that is just called 500,000. So those are problems that are going to distort the results. And if you do cross correlations, it's going to look different. We're going to get there pretty soon. But first, let's create a random test set. There's another problem: bias. If you make a random test set by just taking random 20% of them to be testing, then, all right, you get possible random values. But if you run it again, you'll get different random values. And this is what would seem, as in a research scientist, this is what I do: pick some random samples, then pick some other random samples. That's the way to be unbiased. The problem is, it's not really the way to be unbiased. So let's consider something else, like voting or something that depends on your sex. The human population is 51% women. So if you have a population that's 51% women and you make random samples, then your sample is most likely to be 51% women, but it has a pretty high chance of being 55% women or 48% women. And if it really matters how many of them are women, then if you randomly are unlucky and get here, then your test set is not representative of the population. So doing random sampling is not really the best way to do the job. The way to do the job is stratified sampling. You separate. And it turns out, as we're going to see, as you would imagine, the number one predictor of the price of a house is the income of the people that live there. high correlation. So we don't want to just do random sampling of income. We want to break the income into 5 buckets and then make sure we have exactly the expected number of people in each of those buckets, of samples in each of those buckets. So our sample is not biased. Here's the population in the 5 categories of income. And so instead of just randomly choosing them, we're going to choose just enough to have exactly this many percent in this bucket and this many percent in that bucket, and so on. And so you can see here's where we split the data um, by doing this stratified sampling. Instead of being random and taking a random 20%, we carefully take the correct number from each bin. So the training set is 35% category 3, and the test set is also 35% category 3, and so on. That's stratified sampling, which, by the way, makes me a little nervous. Clearly, there is some degree of bias here. We've sort of mixed the conclusion into how we chose the data, and we're going to see a lot more of this as we go ahead. Now, here's what would happen if you made a test set randomly. It would not have this precise layout, just 3% in category 1, and this one just 3% in category 1. If you make a random one, then, well, I'm not going to worry about it right now. Anyway, let's skip ahead, the unstratified test set. So now we have to remove the income category column and get it out of there. Let me get that. I think we can skip the intermediate steps, but we have to do this one. All right. Now, we're going to visualize the data. This is where we're going to see some more massaging we have to do of the data. All right. This shows the layout of houses by zones by latitude and longitude. And as you see, it has these dense regions where the dots overlap, and you don't really see how many things are there because the overlap blurs it out. So it would be better if we use transparent dots. So let's try that. We use transparent dots. Now you can see more clearly a huge density near San Francisco and a huge density near Los Angeles and not much elsewhere. You can also include population and price to see what you're dealing with here. And so now you have the house value is the color, and you can see the expensive houses are in San Francisco and Los Angeles, and they're cheaper inland and such. So you're getting a lot of information there. But that's one way to examine data. But the way that's going to turn out to be most important to us is to look at the cross correlations, or the correlations here. So here's the correlation matrix. Here's how much these things are predictive of house value. So house value is, of course, 100% predictive of itself. Income is like 68% correlated, so that's very strong. All the rest is pretty much small change. Rooms is 13%, and median age is maybe 10%. And here's the negative 13% on latitude. So the rest of it, almost no predictive power. So the original parameters to predict the thing we're trying to predict, the most important thing is income, and you have a couple of others that are somewhat useful. But you can do scatter plots to analyze these and see things we're going to have to correct here. Okay, so here we have correlations of one thing. Here's house value, the thing we're trying to predict. And so house value against house value, that's just a histogram. Here's house value against income. And as you can see, a very strong linear correlation. This is very predictive. Here we have house value against total rooms. Doesn't look like much. Against median age, doesn't look like there's much correlation. Here's median income and total rooms. Anyways, there's some scatter plots. All right, they make it obvious that median income has a large effect, and the other two parameters have almost no effect. Now, let's look at the scatter plot of median income and house value in more detail. Okay, now you see a clear increasing trend, but you also see a huge problem up here at 500,000. This is not accurate data. This is a defect in the data. So we're going to have to remove these data points, or we're going to train our model to do something stupid. And you can see echoes of it. There's apparently a round off at 450 and a round off at 350, where a bunch of things are shoved into that category that don't belong there. So these are other things that really should be, you should either remove this data or you should alter this data to put it over where it belongs if you want to catch the actual trend of the population. And that's just a human judgment. That's, me not believing this. And I can't really prove that this isn't true. I can just sort of deduce there appears to be a defect in the data and I better clean it off. And now here's a really interesting one. You have like 9 parameters you've measured, and some of those parameters are not predictive of value, but it turns out you can make synthetic parameters by combining the ones that are there that are more valuable. So I calculate rooms per house by taking total rooms over households and bedrooms ratio by taking bedrooms over rooms and people per house. And now if I do that, rooms per house is 14% correlated with the answer more than any other parameter. So this is an issue. Since you have real measurements and these parameters are not really in any sense the ideal things to measure, you can create synthetic data from the data points you have that may be more useful than the data points you have. And this is going to come back a lot later. So, all right, that's an example of some of the things that go into it. And if you think about like trying to predict who's going to win an election from samples, it has all these judgments. You try to select poor people, rich people, urban people, uh, rural city people, and you try to get the right mix and you try to guess how to sample and how to correct for bias. And there's just a whole lot of judgment that goes in there that is not from the machine. So that's the kind of stuff you have to do to prepare your data. So let me stop this one.